First, let's look at the title of Module 2, Second Order Linear ODEs. And there is another topic, Introduction to Laplace Transform. This semester, this year I modified because the last year I started Laplace Transform after midterm. So then I feel I do not have enough time to cover the important topics. Laplace transform and Fourier analysis, these two important topics. So this year I plan to move Laplace transform before midterm. So then Fourier analysis after midterm. So then we can have more time to work on these two most important topics. All right. So then Laplace transform, I plan to split, introduction part, relatively easy part, Laplace transform, then combine with module 2. Then, relatively advanced part, then I combine with module 3. So module 2 and 3, so each one half of the Laplace transform. So after first 3 modules, we start midterm. Okay? We start the midterm. Before or after spring break. So I can double check. All right. So today, part A, homogeneous second order linear ODE. We did a little bit homogeneous first order. Remember the last time, homogeneous first order. But this time, we need to study more homogeneous second order. The reason, I will explain the reason why we study the homogeneous version. Today, I will spend quite some time on this, why we need to study homogeneous type linear ODEs. 8.1 Properties of second order linear ODEs. First, let's study the definition of linear second order linear ODEs. Remember, we learned the definition of first order, right? Recall a little bit. Similar. The definition is similar. But I need to give you a very clear description for the definition. The standard form of second order linear homogeneous ODE. So we consider this standard form. Although you will see some more general form, but more general form, similar to our first order ODE. The more general form, most of the equations we cannot find the solutions. For second order, the same situation. For most of the general second order ODEs, we couldn't find the analytic solutions. So we need to use other ways, numerical way. So I mentioned last time, computer algorithm, numerical ways to find a solution most of the time. All right. But here, this course, our main focus, we will learn problem-solving techniques, finding analytic solutions. Not numerical solutions, analytic solutions. For some special equation types. So this one, standard form. Okay, all right. Right-hand side, you can see 0. Right-hand side equals 0. That corresponds to the homogeneous version. Homogeneous, we mean, the right-hand side. Left-hand side part, you can see you have y prime term, y prime. All right, But this standard form just single y double prime, y double prime, single y double prime. Its coefficient is 1 for the standard form. Then y prime, you have y prime term, so its coefficient, a function, p function. Then y term, its coefficient q function. But other than those three terms, 0. The remaining 0. So that's the homogeneous version. Yeah. All right. If it's non-zero, yeah, later we will move to the right-hand side, R function, PQR, right? So the R function, non-zero function, then that's the non-homogeneous function. Yeah, so we will go there. Yeah, because homogeneous version easier. So let's work on the easier version first. Yeah. Later, yeah, then harder, more general version. Yeah. All right. First, let's understand the linearity properties for the second order homogeneous linear ODE. Yeah. Yeah. Linearity property. Let's look at that. Yeah. This simple property, very, very important. Yeah. All right. So what's that? Yeah. So here, regarding, yeah, because how do you define linear second order ODEs? Yeah. So here, based on the linearity properties in these three cases, 1, 2, 3. Yeah. Let's look at the first case. First case, all right, the coefficient of y double prime cannot contain y prime or y. Okay, coefficient of y double prime cannot contain y or y prime. Yeah. Otherwise, we don't call it linear. Okay, yeah, that's the first condition. Yeah. The second condition, yeah, all right, so here, yeah, the first one, with respect to y double prime, it is a linear function. Then, further explanation. Yeah. So the coefficient of y double prime could be a function of x, but it cannot contain y prime or y. Yeah. Could be a pure function of x. Yeah. That's legal. Yeah. Regarding the linearity, that's legal. Yeah. Similarly, with respect to y prime, it is a linear function. Okay, yeah. Then it's the coefficient of y prime cannot contain y double prime or y. Yeah, similar requirement. Yeah. But this time we focus on y prime, particular symbol. Yeah. All right. Yeah. Then the third one, with respect to y, it is a linear function. Yeah. Coefficient cannot contain y and y double prime or y prime. Yeah. That's the, if these three requirements are satisfied. Yeah. So then we, make sure the right hand side is 0. Okay? Yeah. Because sometimes you are given a function, these three conditions are satisfied, but right hand side is not 0, it's 1. If the right hand side is 1, you cannot call it linear ODE. Okay? That 1 will break the linearity. Yeah, later I will show you that simple example. Okay? Right hand side must be 0. Yeah. If it's 1, yeah. Later I will give you a counter example. So that property will break the linearity property. Yeah. You won't get a linear ODE. Okay? Yeah. Yeah. All right. Let me show you a few simple examples. Yeah. The first example, yeah, let's look at this equation. Yeah. You can check these three conditions. Yeah. You can see all the three requirements are satisfied, right? Yeah. So we can say, and right hand side 0. So we can say this is a linear second order ODE. Yeah. Right. Yeah. So the answer is clear. Yeah. Standard. Yeah. But although this is linear second order, but it's not a standard form. Yeah. Sometimes if you want, you can convert it to standard form. Yeah. So you just divide it by x both sides. Yeah. After that conversion, yeah, you get a standard form. But because you did a division by x, yeah, then you need to consider the standard form and the original form. If they are equivalent, they could be slightly different. Yeah. So here, regarding the equivalence of these two equations, because the original equation, it is allowed, x is allowed to be 0, right? Yeah. In original equation, x is allowed to be 0. But in the standard form, second form, x is not allowed to be 0. Okay, that's the key difference. Yeah. But because the difference is small, you can work on the standard form first. After you get a solution for the second, standard form. Not done yet. You need to bridge the gap. There is a small gap, right? X equals 0. It's a small gap. So the last step, you need to find a way to bridge that small gap. Because your goal, you want to go back. You want to find a solution for the original equation. Excuse me. Yeah, so be careful. All right. Yeah. Here, our answer about the linear ODE or not. Answer is yes. Then, second, now you tell me, is it linear second order ODE? No. Yeah. Violation, you can see first term, second term, two violations. First term, there is a violation because the coefficient, if you look at the y double prime term, coefficient contains y. Yeah. If you look at the y term, the coefficient contains y double prime. Right? So that's the violation. Second, yeah, because that square is a violation. Okay? Yeah. So then, not a linear ODE. Yeah. If it's not a linear ODE, then it could be much harder to solve. Yeah. So we do not have many methods to solve nonlinear ODEs. Yeah. So for nonlinear, then people most of the time rely on numerical methods. Yeah, computer programs. Yeah. All right. Yeah. So the answer is no. Yeah. Question. Yeah. So now I answer that. Why it is important to study second order linear homogeneous ODEs? Yeah. Because the goal. Yeah. We need to look at the goal. Yeah. The goal. We want to find all the solutions, right? So when we need to solve second order linear ODE, we want to find all the possible solutions. Yeah. But when we study homogeneous second order linear ODE, it gives us a way to find all the solutions. Through homogeneous, we cover all possible solutions. Yeah, so you will see it. Yeah. All right, here, superposition principle or linearity principle. Yeah, I already, this principle, very simple, yeah, but it is important. Now let's consider the homogeneous linear second order ODE. Yeah. First, let's check the linearity. Yeah. So we call it linear ODE. Then it must have the linearity principle. So we want to verify it, right? Yeah. So let us assume y1 of x, this function, two functions, and y2 of x function. These two functions are two solutions of the above ODE. Okay, we just assume there are two solutions already known. Now we want to study how to use these two solutions to get more other solutions. Because remember our goal, we want to cover all the possible solutions. Yeah. So let us use these two known solutions to get more other solutions. So the first one, because y1 is the solution, we plug in y1 into the, homogeneous second order form. Yeah, we get a first equation, first equality. Let's say, because we know the solution, right? Yeah, equality. Second, similarly, and a second equality. All right. Then we combine these two equations. We combine these two equalities. Yeah, we know both true. Yeah. Now, when we combine, we use the linear combination. That concept, linear combination concept. Yeah. So let me recall it a little bit. What is the linear combination concept? Yeah, we talk about linear combination concept, right? Yeah. All right. So here, yeah. Let me explain the general linear combination concept. Suppose we have two variables, x and y, two variables. Now we want to form a linear combination representation of these two variables. Yeah. So then we choose two constants, a and b. A times x plus b times y. That is the, linear combination of x and y. Yeah. A constant times x plus b constant times y. Yeah. All right. So here we want to do the similar combination way. Yeah. C1 constant times first equality plus C2 constant times second equality, then adding together. Yeah. We still get an equality, right? Yeah. By the algebraic property, we still get a new equality. Yeah. So then we combine the terms. Yeah. Yeah. We combine the like terms. Yeah. Now you can see inside the parenthesis, we get a new expression. That's the linear combination of y1, y2, right? Yeah, based on our definition. Yeah, linear combination here. Let me write it clear. Linear combination. Okay, yeah, concept. So you can see this linear combination form just gives us a new solution, right? Yeah, because it satisfies the original equation. That means two known solutions, y1, y2, help us to get more new solutions. How about that? Because we have freedom to choose C1, C2, right? Yeah. C1 is 5, C2 is 11. Yeah. So 5 y1 plus 11 y2, we get another solution. So you can see, we can cover infinite many solutions, right, through linear combination way. Okay, all right? Yeah. That's the importance of the linearity principle. If your equation does not have the linearity property, then this linear combination way would fail. Okay? Linear combination way won't work because your original equation does not have the linearity property. That's why homogeneous form is important. For non-homogeneous form, there is no linearity property. Yeah. Then you cannot use linear combination to get more solutions. Yeah, I will show you that simple example soon. Yeah, all right. Yeah, so the conclusion. Yeah, any linear combination of y1 and y2 is also a solution of the above ODE. The conclusion. Yeah. So this explains why we need to study homogeneous linear second order ODE. Yeah. Okay? Yeah. All right. This principle does not hold for non-homogeneous linear or non-linear ODEs. Yeah. Non-homogeneous. Yeah. Never try that linear rating property. Okay, for non-homogeneous. Yeah. Yeah. Let's use a simple example. This is a simple example, right? Y double prime plus y, left hand side, you can see satisfy those three requirements. Unfortunately, right hand side is not 0, it's 1. That the linearity property breaks. You won't get that linearity property. Yeah. Let's plug in y1, y2. Okay, let's assume we have y1, y2. Yeah. All right. Yeah. y1, 1 plus cosine x. Yeah, you can plug in, verify it. Yeah. y1 plus cosine x satisfies the original equation. Yeah. y2, negative cosine x. So if you plug in, you get a second solution of the original equation. Yeah. But now we want to take a linear combination of y1, y2. Linear combination. Then we want to plug in. If the linear combination of y1, y2 also gives us a new solution. You will see. No. Okay? All right. Yeah. Sorry. Yeah, y2 is that. Yeah. I confused. Yeah, I'm sorry. Yeah, now I see y2. Yeah, it's a y1. Here, the reason I calculate y double prime, because I want to verify if it satisfies the solution. All right? Yeah, it's not the second solution. Yeah, sorry. Yeah, now y2 is the second solution. All right? Y plus sine. Yeah, because double prime. Now you plug in. All right? Yeah. So it's very easy to verify. Yeah, adding together, right? Adding together, cancel out. Yeah. All right. Yeah. So I didn't notice that. Yeah. All right. Now, you agree there are two special solutions. No, not general. No, not general. Later we will call particular solution. These two solutions we call, each one is a particular solution. Yeah. All right. Now, let us add up these two solutions. y3 equals y1 plus y2. All right? Yeah. So now you want to verify if y3 is also a new solution or not. Yeah. So you take double prime, right? Yeah. Adding together, yeah. But you get it. y3 double prime plus y3 equals 2. Not a 1, right? It's 2. Yeah. So it does not satisfy the original equation. Yeah. Close, but we cannot call it what? A new solution. y3 is not a solution. Okay? Yeah. Then this linearity property fails. Okay? Yeah. So that's the reason for non-homogeneous, never apply that linearity principle. Yeah. All right. Yeah. So that's the main point here. Yeah. Next, now we talk about particular solution for second order. Yeah. Particular. Yeah. Yeah. Our goal, we want to find a general solution. Yeah. But here, let's study the relationship between a general solution and a particular solution. second order linear. Now, this time, yeah, when we talk about particular solution, we consider non-homogeneous ODE. All right. The standard form for non-homogeneous second order linear ODE. Yeah. Linear ODE. Yeah. Initial value problem. Yeah. So this is the second order linear ODE. Yeah. But so here, let me clarify. So do not get confused. Yeah. Because when we check our previous slide, three requirements, yeah, for y double prime, for y prime, for y, yeah, so all three requirements are satisfied. All right. So we call this equation as is a linear ODE. Okay. All right. Then, when you move another step, then you need to separate, yeah, in this way. Separate, that means this linear ODE does not satisfy that linearity principle because it's non-homogeneous. Okay, so you cannot apply our previously mentioned linearity principle on this linear ODE. Although it's linear, we call it linear, but we cannot apply our linearity principle. Yeah, remember the previous slide. Right? We also call superposition principle. Okay? Superposition or linearity principle. Yeah. But you cannot apply on this linear ODE. Okay? Yeah. Because people tend to feel, because it's linear, so then we can apply linearity principle. Yeah. So separate. Yeah. Both, you see the linear word appear both places. Yeah. Yeah. But their meanings are different. All right. Yeah. Initial values. Yeah. Because we need to, this time we consider initial values. Y of x0 equals the first constant, capital K1. Then y prime of x0 equals second constant, capital K2. Yeah. So in order to solve a second order linear ODE, the initial condition, you need to have these two conditions. If you have one, it's not enough. For first order, we have one. Now, first order, one is enough. Y of x0 is a constant, then we can solve the first order. For second order, you need two initial conditions. Third order, you need three initial conditions. And nth order, you need n initial conditions. Yeah. Yeah. Later, we will move to n, order n, higher order ODEs. All right. Goal, this time, find a general solution for the above IVP, initial value problem. Yeah. All right. Revisit old example. Yeah. So here, remember, yeah, in this example, we just see the linearity principle, does not hold here in this one. Yeah. All right. But I want to use this example to show you, yeah. Because remember we found two particular solutions, right? There are two particular solutions. All right. Yeah. All right. Simple solution. Let's pick one. Yeah. We don't need two. Yeah. We only need one particular solution. Yeah. Here, yeah. This one is simpler, right? Y equals 1 is a solution. Because y double prime, 0. So left hand side 1, right hand side also 1. Yeah. This one is the simplest particular solution. Yeah. All right. So let's take this, and we use y0 to represent this particular solution. Yeah. Yeah. So here you can see, to solve non-homogeneous second order linear ODE. Our first thing, yeah, so we need, yeah, there are two steps. Yeah, all right. Solving homogeneous version, that's one step. But other than that, there is another step. Find one particular solution. You only need one particular solution. Okay? Yeah. But here, we find one, the simplest one, y0 equals 1. Yeah. All right. The next thing, how to use this particular solution. Yeah. To give us more solutions. This one, only one. We only need one. Yeah. All right. The verification. Yeah. All right. Now we consider a new function. This new function is u function equals y minus that particular solution, y0. Minus y0. This u function, yeah, if you use this new u function, you will, if you plug in into the original equation, you will get a homogeneous version, but for the u function, not the y function. Yeah, you convert. So you use this subtraction form. Okay. Yeah. Y, that's the solution for the original equation. Yeah. But we take subtraction with one particular solution. Okay. Any solution y subtracts just one particular solution, y0, that difference function will be the solution of the homogeneous version of the original second order linear ODE. Yeah. So this time you take u, now that right hand side 1 is gone, so you have the y double prime plus u equals 0. Okay? Yeah. Think about it. Because you plug in y, right hand side 1, you plug in y0, right hand side also 1, you do subtraction. Okay? Yeah. So 1 minus 1, 0, right hand side. Right hand side becomes 0. 1 minus 1. Yeah. Left hand side, you get a u double prime plus u. Yeah. Next question. Can you solve this this homogeneous second order linear ODE? If you can solve and use the linear combination to cover all possible solutions, then last step, you can write the general solution for the original non-homogeneous second order ODE. Yeah. That process. Yeah. All right. Yeah. So with a general solution, what's the general solution? The general solution here is u equals c1 times cosine x plus c2 times cosine x. Yeah. Why? Yeah, here. Why? Explain why. Yeah. I have several slides I need to use to explain the foundation. Why? Okay? Yeah. At this point, just be patient a little bit. Yeah. Because there is some fundamental theory behind it. First, why? The first thing is cosine of x is a solution of this u equation, right? Cosine x. Double prime negative cosine x plus cosine x 0. Sine x is another special solution, right? Of that u double prime plus u equals 0. Double prime negative sine x, so they add together 0. All right? So two solutions. Now we use the linear combination c1 times cosine x plus c2 times sine x. Linear combination, we know it's also a solution, right? Yeah. So now we call this the general solution of that homogeneous version, u double prime plus u equation. Yeah. If we want to go back to the original, can we just add u0 back to u0, y0, add it to this u function, we get a general y function solution, right? Yeah. because y equals u plus y0. Yeah, you add it back because you did subtraction before. When you want to get the final solution, you need to add that back. Okay, add that y0 function back. Yeah, to your u function. So you get a final solution of the non-homogeneous version of the second order linear ODE. Yeah. Yeah. All right. Yeah. Yeah. But later I will explain more theory. Yeah. Why we can use this way to cover, all the general solutions. Yeah. Yeah. I will use, some new concepts to explain. Yeah. All right. Yeah. So here you can see, the final solution. Yeah. All right. So now after this simple example, now I hope you can understand why we need to solve this homogeneous version of the original ODE first. Yeah. Yeah. All right. Yeah. Okay. Yeah. What is the relationship between these two? Yeah. So this example already showed the relationship, right? Yeah. All right. Then I want to explain. Yeah. So here, this 8.2 topic, a little bit theoretical and abstract. Yeah, because I need to explain the foundation of the theory. Yeah. Why we can do it that way? Why we can do the linear combination way? Right? We know it is a solution. Yeah. But the question is, if we can cover all the possible solutions, do we miss any solution? Right? We want to cover all the possible solutions. That's the point. Yeah. Yeah. Because from the discussion in our 8.1, the linear combination of two solutions, y1, y2, will give us new solutions. Yeah. So all the linear combination forms, we know there are a lot. All those solutions, all those representations will give us new solutions. But there is one question unknown. One question unknown. Yeah. Here, pay attention to the logic. Okay? Pay attention to the logic. Yeah. Suppose we have a second order ODE. Okay? Yeah. So here I assume we have second order linear ODE. Yeah. We want to find all the possible solutions. That's our goal. Okay. All right. Here, let me draw a circle represent all the solutions. Okay. Yeah. Represent all the solutions. All right. Yeah. Circle. What do we have? We have y1, okay? Yeah. And we have y2. Two different solutions. Yeah. After that, we know we can use linear combination to form new solutions. So here, I draw a smaller circle inside this big circle to represent the linear combination C1y1 plus C2y2. Okay. We know all the points inside the small circles, they are solutions of the original equations. Okay? Yeah. Linear, yeah. Let's assume homogeneous, because this linear combination only works for homogeneous, right? Yeah. Homogeneous. Right? Only works for homogeneous. Yeah. All right. But the question is, do you get all of the solution? You use a linear combination. Can you cover all the possible solutions? Yeah. Is there any solutions? You still have some solutions in the big circle, but not in the smaller linear combination circle, right? You don't know. You don't know, right? If the linear combination circle can cover all the solutions in the big circle, right? Is it possible you have a chance to find some other solutions? Those solutions cannot be represented by the linear combination of y1, y2. That's the question. We don't know. We don't know. Yeah. Yeah, but this section, 8.2, we need to answer that question. Yeah. The answer is no, no other solutions. Yeah. That's a great result. Okay? That means we use linear combination where we can cover all the possible solutions. Yeah. Yeah. Very nice. We won't miss anyone. Yeah. But you need some solid theory behind it. Yeah. So this section we will learn that. Solid theory. Yeah. All right. Yeah. So let me start. Yeah. Before the break, let me start. The form of general solution. Yeah. Initial value problem. Yeah. All right. Assume y0 is a particular solution. Yeah. Okay. Yeah. So we plug in y0. Yeah. We get that equality. Yeah. Then we consider u equals y minus y0. Yeah. We just repeat the idea in our previous slide. But this time we work on the general form. Yeah. All right. So you plug in, this u function satisfy the homogeneous version of the original equation. Yeah. Okay. All right. Need to find two different solutions for the homogeneous equation, y1, y2. Okay. All right. Yeah. What condition do we need for y1, y2? Yeah. Yeah. You find y2. You plug in y1 into the homogeneous equation, you should get an equality. Also, y2 you plug in, you also get an equality, right? Two equalities. Yeah. All right. How different they should be? Yes, another question. Because y1, y2, here you consider two different solutions. y1, y2, two different. Yeah. If y1, y2 the same, then, it does not make sense, right? Yeah, because, one function you repeat it twice, Yeah, it does not help. Yeah. The thing is, it does not help. Okay, so you want y1, y2 different. At least the y1 must be different, right? Yeah. But when you say y1, y2 different, the second question is how different they should be. Another question: how different? Yeah. Yeah. Because two functions are different. They could be slightly different, right? They could be, significantly different. Yeah. Slightly different. Yeah. The shape is the same. Okay. You just shift a little bit. Yeah. Yeah. The shape exactly the same. Okay. Slightly different. Completely different. The shape of the two functions completely different. Yeah. So we want to see how much is the difference? How big is the difference, right? If the difference is small, then it does not help, right? So we want these two functions must be, significantly different. Yeah. But we need to use solid mathematical description. We cannot say, completely different. What do you mean completely different, right? So we need to use some solid mathematical concept to describe their difference. Yeah. So we need to introduce that concept. All right. All right. Consider special case. Now, Let's consider y2 equals constant. K is a constant. Constant, non-zero. Let's say K is a non-zero constant. If y2 equals K times y1, if K not equal to 1, y2 is different from y1, right? But if it is this y1, because it is just the scaled y1, right? You scale y1 by constant K. It does not help. Okay? Yeah? Because the relationship too close. y2 and y1 too close. Okay? Yeah. So you use two objects so close, one just the scale of the other one, then after you do linear combination, still the new solution also a scaled version of one of the two, right? Yeah. Because both scaled version, you get a new, still scaled version of y1. So you won't get a completely new solution. You just scale one solution, you know, more or less. So that's not meaningful work, right? That's not meaningful work. So that does not help. We want to avoid that, okay? So we don't want to choose y2, which is a scaled version of y1. We want to avoid that. Yeah. But we need to use a new mathematical concept to tell us if y2 is okay or not. Okay? Yeah. So that concept of linear dependence, linear independence, that concept. Linear, yeah. So this case, y2, y1, if it satisfies this condition, yeah, y2 equals k times y, we call it y2 and y1 are linearly dependent. They are linearly dependent, okay? Because y2 is a linear form of y1, right? K times y1, it's a linear, right? Yeah. Linear version. Yeah, linear relationship, okay? y2 is linear with respect to y1. Yeah. They are linearly dependent. If they are linearly dependent, then we just use one function to represent that whole class of scaled solution, right? We just use y1 to represent all those scaled version of y1 solution. Yes, yes, homogeneous, yeah, all right. Yeah, homogeneous, yeah, because if you have k non-homogeneous there, your k won't work. Yeah, good, yeah, homogeneous. Because here we're talking about homogeneous version. All right, yeah. All right, yeah. So the next, yeah, it does not help because ky1 is automatically a solution of the homogeneous equation. Yeah, we don't need to do anything. Every time if y1 is a solution, then ky must be another solution of that homogeneous equation. Yeah. All right, so it does not help. Okay, yeah. We just use y1 as a representative, okay? All those k times y1 can be represented by a single y1. That's good enough. Yeah. All right. Yeah. Let us take a 10-minute break. Yeah. Yeah. Because before the break time, we should not talk about some important concept. After you come back from the break, then we study the linear independence concept. That is an important concept. Okay.